Okay, so it is my great pleasure to present Federica Fanoni from Université de Paris-Est in Créteil, and Federica is going to tell us about orthosystoles of surfaces with boundary. Federica.
Yeah. So thanks a lot for the invitation. Very happy to be at this conference. And as I was saying before, Ara was not aware when he and Ruben invited me that I was going to talk about joint work with him. So it's not his fault. Okay, so the work of today involves orthogeodesics on compact surfaces as boundary. So for this talk, there's no infinite type surfaces. So I'm going to consider compact hyperbolic surfaces, and I'm going to always assume that their boundary is non-empty, and the boundary is going to be a union of simple closed geodesics. And what are orthogeodesics? Well, orthogeodesics are geodesics on the surface that start from the boundary, go somewhere in the surface, and go back to the boundary. And as the name says, orthogeodesics, I require that they are orthogonal to the boundary. So just for a couple of drawings, one could start somewhere. They're not necessarily simple. They start somewhere and they go somewhere else. They can also start and end at the same boundary component. There's a whole load of such geodesics. And well, the title says orthosystoles. So what is an orthosystole? It's a special orthogeodesic. It's the shortest orthogeodesic. So it's something that realizes the minimum of all lengths of all orthogeodesics. So that means, say, if I write it in word in formulas, it's some orthogeodesic such that the length, so there's always going to be my notation for the length of this orthogeodesic, is the minimum over all orthogeodesics in the surface of the length of these orthogeodesics. And by abusing notation, we're actually going to call orthosystoles also the length of such a curve, and we're going to denote it by OSys of X. So an orthosystole is either a shortest orthogeodesic or its length. So possibly many of you are more familiar with the concept of systole, which is where the name comes from. So a systole is a shortest instead closed geodesic. Shortest closed geodesic on a surface, and here, since we are considering surfaces with boundary, we're going to assume that it's not a boundary component. And as before, we denote, so similar to before, we can denote by sys of X the shortest, the length also of such a thing. So the minimum of the length of alpha, or alpha is a closed geodesic.
Sorry, Federica,
yep.
Can I ask you a question?
Sure.
Maybe I'm saying something completely wrong, but shouldn't you also ask that it's not homotopically trivial?
Since I'm already asking that they are geodesic, no. So on hyperbolic surfaces, closed geodesics are going to be essential.
Okay.
Yeah.
Thank you very much.
Yeah, but so yes, an alternative way of looking at this is to look at the essential simple closed curves, so things that are not contractible or homotopic to a boundary component, and then look at the minimum among those, of the length among all of those. Okay, so the systole is this, and to follow this name, we call the orthosystole the length or a shortest orthogeodesic. And something that is also often studied for surfaces in relation to the systole is what is called the kissing number, which we denote by kiss of X. And this is just the number of systoles of the hyperbolic surface. So generically it will be 1, but it could be much more. And so with this in mind, we decided to call the orthokissing number and denoted by OKISS the number of orthosystoles of X. Okay, so these are the main characters. And the main thing we're interested in doing is studying bounds and extrema for the orthosystole function. So here, what am I considering here? This is the moduli space of surfaces. So I fix S surface, let's say of negative Euler characteristic, since I do want it to have hyperbolic structure, and of signature Gn. So the signature is G is the genus and N is the number of boundary components, assuming no cusps. So this moduli space is the set of all hyperbolic surfaces which are homeomorphic to this base surface. And here I have these numbers. These are numbers L1 to Ln. So I require that the boundary components have length L1 till Ln. And all of this is up to isometry. So here the function is the function that the orthosystole function is just a function that, given such a surface, associates the orthosystole of the surface. And we're interested in understanding what are upper and lower bounds and whether these can be realized, what are surfaces that realize these bounds. And just one comment, this space, this moduli space is big. So it has, well, it is not a manifold, but its universal cover is a manifold that has dimension 6G minus 6 plus 2n. So it's a big space, and so it makes sense to have a function and look at its values on that. Okay, so the first thing is I said that I fixed the boundary length of my surface. So one might wonder why. And the answer is because otherwise the problem we're asking is trivial. So otherwise what we could look at is the orthosystole function on the moduli space of S, where I'm not fixing the boundary lengths, I'm letting them go as I want. And then this function has supremum equal infinite and infimum equals 0. So, well, we have the bounds, but it's not very interesting. And the main idea of why this is true is the color lemma, is due to the color lemma. Whoops. So this tells us that if I have X, a simple closed geodesic on a hyperbolic surface X, then there is an embedded half or full color, the ones that Dragomir was talking about a second ago, embedded, the standard ones, embedded half if the curve is a boundary curve, color of width that depends on just on the length of the curve, and in particular this width goes to so this goes to 0 if the length of the curve goes to infinity, and goes to infinity if the length of the curve goes to 0. So essentially the idea is if you have a very short boundary component, you will have a very large color embedded. This is very long. So if we let all the lengths go to 0, any orthogeodesic will have to cross this color, so will be very long, and in the limit it will be the supremum will be infinite. And conversely, if I have a very long boundary component and I have some pair of pants with short boundary geodesic and then the rest of my surface, I will always get some orthogeodesic here, which is very short. And very short means that actually if I let the length of this boundary component go to infinity and the length of these two curves go to 0, this actually will go to 0. So this will give us the infima. Okay, so this hopefully justifies why we want to fix the boundary length. And an extra remark is that for the same reason, when we fix boundary length, we already have what is actually a sharp lower bound. So the color lemma already gives us a sharp lower bound for the orthosystole function on the moduli space where we fix the boundary length. Essentially, we can realize the length that's twice the color width. And so this means that actually the question we're mostly interested in is what is an upper bound for this orthosystole length. And the first lemma is that there's an upper bound of this form. So I fix the signature and I fix the boundary length. Ln is the longest boundary length. And if I pick a surface in this moduli space, then there is this upper bound, which is very explicit. And what's maybe most interesting is to see how it grows. So this grows as 2 log g once as when g goes to infinity. If we keep n, the number of boundary components, and the length fixed, and li fixed. And in case you've ever seen the proof, so there's a very similar upper bound in a sense for the systole length, and it's because here the idea for the proof of this lemma is exactly the same. So this is an area argument. The idea is as follows. So I start with my boundary length, boundary curve of length ln, and I can start growing a color of some width. Now, not necessarily the one given by the color width, color lemma. And so for as long, so if this color is embedded, meaning it really still looks like a cylinder, then we can compute the area. Then, so it has area ln times sinh of w. And of course, if this is embedded, it just needs to be smaller than the area of the surface. The area of the surface can be expressed as it's 2 pi, the Euler characteristic. So it's the thing we see on top. So this gives us an upper bound for w being embedded, and the point is, at the first point in which the color is not embedded anymore. So if w is the smallest, so that the color is not embedded, or cannot be prolonged to be embedded, we have 2 cases. Either we have gotten to some other boundary component, we've gotten somewhere here, and then we have an orthogeodesic here of length w, or at most w. And the alternative is that this actually, no, the drawing is going to be less pretty, but that this color starts having some self-intersection, and then you get some orthogeodesic here, which has length 2W. So then you just put the bound for W and these bounds together, and you get the upper bound. So that was not the hard part. A couple of extra things we can say pretty easily about orthosystoles is that they must be simple, so they cannot self-intersect. And furthermore, they need to be pairwise disjoint. So the first thing is similar to what systoles do. The second one is different. In the case of systoles, they can intersect, and here it's different. So this is, again, this is some surgery argument. For both points, it's essentially the same. So the idea is you start with your orthogeodesic, you assume it self-intersects, for instance, and then it does something else, and it arrives at that's maybe the same boundary component, maybe a different one. And the point is, you can just follow this and forget this first loop and then go to the next. You're gonna get a shortest curve, then you just straighten it and you get the shortest shorter orthogeodesic. So you can always decrease the number of self-intersections until you don't have any more. So this tells us in particular that there is an easy upper bound on the ortho kissing number, because it's easy to check how many such arcs can be pairwise, many such simple arcs can be pairwise disjoint. So here I'm just going to say what we mean by a hexagon decomposition. So a hexagon decomposition is a maximal collection. Oops. Of pairwise disjoint simple orthogeodesics. And what's easy to say is that such a collection is maximal only if it decomposes the surface into the smallest possible pieces. And in this case, these are hexagons, this is what gives the name. So this is a collection, is the same as a collection of pairwise disjoint simple orthogeodesics cutting the surface into hyperbolic rectangle hexagons. And then once we know that these two things are the same, by an Euler characteristic argument, this is just Euler characteristic, we see that this is the same a collection, like as before, of pairwise disjoint simple orthogeodesics of cardinality exactly the bound that I put up there. So what this corollary is telling us is since they are disjoint, they can be at most this many. And here, just maybe an example of a hexagon decomposition, so that if you're bored, something you can do is to try to understand why this cuts the surface into hexagons. You can choose these curves here. They're not supposed to start at the same point, but it's even harder on a tablet than on a blackboard. Okay. But these 6 arcs are going to split the surface into a collection of right-angled hexagons. Okay, so the maximum, the biggest amount of orthosystoles that we can have is this one, and in this case, they form a hexagon decomposition. So I can tell you now what the main result is. It comes in two parts. I'm going to tell you here on this slide about the first part, and the first part is about the case of a single boundary component, which is in which we have a much better answer of what's actually happening. So in this case, there's an equivalence between a bunch of statements. The first is that if I have a surface, this is a local maximum for the orthosystole function. The second is actually that this surface has the maximal possible number of orthosystoles. So this is telling me that X has a hexagon decomposition of orthosystoles. But this is actually equivalent to being a global maximum for the orthosystole function. And it's equivalent to having this orthosystole length that we can explicitly compute. And it's a function of course, of L, the boundary length, and of the genus. So let me just give you a couple of remarks about this. So of course, this bound doesn't look very pretty, but the nice thing is that, so this is some function, let's call it f of g and L. And if L is fixed and g goes to infinity, then this function grows exactly like 2 log g. It's asymptotic to 2 log g. So this is the same order of growth as the upper bound. The upper bound that we constructed before, which, I mean, if you think about it, in that upper bound, you have this big color that's almost covering the entire surface. So these are really funny surfaces. And something else is not many, for as much as I know, quantities for which we know the order of growth. For instance, for the systole, this is not known. For the diameter, we know the order of growth of the maximum, the minimum. But this is, for as far as I know, one of the few examples in which we actually know the order of growth of such an extremal value. The second remark is the following. So you probably know of Mumford's criterion. So this tells us that if we look at, it is often denoted epsilon. So for any epsilon, we fix an epsilon, positive epsilon. We look at the moduli space, epsilon, which is the so-called thick part of moduli space, which is the collection of all hyperbolic surfaces in that moduli space, such that the systole is at least epsilon. So Mumford tells us that this is a compact subset of moduli space. And this means, in particular, since the systole function is a continuous function, this makes it easy to show that the systole admits a maximum. So we can use that to show that the systole function admits a maximal in moduli space. So one would want to do something similar for the orthosystole length to easily say that there should be a maximum. And unfortunately, this is not the case. But this is not true. This fact is not true for orthosystole instead of systole. So if we just fix a random epsilon and we look at surfaces where the orthosystole is bigger than this epsilon, this is not in general going to be a compact subset moduli space. So we actually need to work more to show that there are maxima for this function. Okay, so all of these equivalences give us a pretty concrete picture of our surfaces. And this allows us to get a corollary, which is the following. So it's still in the same case, of one boundary component. If you look at the orthosystole function, we know exactly how many local maxima there are. So this is an ugly function. We didn't compute it. So this essentially follows the idea is that the local maxima are the same as the global maxima, so they correspond to these hexagon decompositions. So these topological types of hexagon decompositions. Now I'm being a bit vague, but decomposition, sorry. And these topological types have been counted, and this is the number that comes out. So these are counted by Bacher and Federica. And one reason why I like this corollary is that for the analog question for systoles is wide open. So for the systole, what is wide open is, well, for one thing is what is the question of what is the maximum over moduli space, and the second is what are local and global maxima. So how many local and global maxima there are. And some reference to that, for instance, there's a paper of Federica and Rafi, where they construct many local maxima for the systole length, and it's quite a complicated paper. And here we have a complete description of what's happening. Okay. What's the second part of the result? The second part is telling us what happens if instead we have more than one boundary component. So here the result is unfortunately much less precise. We can get surfaces with large orthosystole. So what does large orthosystole mean is that also in this case, so here if we fix N, and the Li are fixed, and we let G going to infinity. So here we have some function H of G and of the Li's. Then this function H grows like 2 log G. So again, we get the same order of growth as the upper bound. What is a bit disappointing is that on the other hand, we do know, or I haven't written down all the details, but we do know that these are not even local maxima. So the surfaces that we construct are not even local maxima for this orthosystole function. But so the surfaces constructed in the theorem are not even local maxima for the orthosystole function. Okay, So what I wanted to do next is give you an idea of what goes into the proof. Is there any question before I go further? Okay, so I guess that's good. Otherwise, interrupt me at any point. So in the first part was where we had one boundary component. And essentially there I was saying a surface is a local maximal if and only if it's a global maximal, if and only if it has a hexagon decomposition of orthosystoles, if and only if it has a certain length. So now let's look, let me make the drawing in the case of genus 1, because I can easily draw a hexagon decomposition. Not that easily, apparently. I think this is correct. We need 3 arcs. So here, if we have a hexagon decomposition and we cut along this, each piece that we're gonna see is a right angle hexagon, where half of the sides are given by our orthogeodesics, and the other half of the sides are given by pieces of the boundary. So if this is an hexagon decomposition of orthosystole, or even if this is a hexagon decomposition of orthogeodesics of the same length, so what is this length? This length, I'll call it A. So all of these green arcs will have length A. And what's happening, this is just a basic fact of a hyperbolic trigonometry, is that if I have such a hyperbolic, such a right angled hexagon, then the other 3 arcs will have the same length, some alpha, which is an explicit function of A. So, I mean, I can write down, I think it's the cosh of alpha is cosh of A over cosh of A minus 1. So it's not very important what that is, but I can explicitly recover alpha from A and vice versa. And the next observation is if I look at the boundary. So the boundary is made by pieces of length alpha. And how many pieces can be computed by looking at how many hexagons I have in my hexagon decomposition. And this is something that one can compute just with Euler characteristic. So I'm not going to make the computation now, or I'm going to make it wrong. But what one can check is that this is given exactly by 12g minus 6 pieces. So this boundary length needs to be 12g minus 6 alpha. So what this is telling us, if you put these 2 things together, is essentially that if you fix L, there's only one, you can solve it, and there's only one A that makes this possible. So this gives us surfaces. So if you fix L and you fix a hexagon decomposition, what you're going to get is a certain length for the curves in your hexagon decomposition. And this gives us candidate surfaces that potentially have large orthosystole, and luckily those are the ones that are actually the maxima. So you can, let's say, given, so this I have hexagon decomposition, I call it H. Given H, L, and G, we can get this A, and we can get a surface X A, where all of the lengths, well, all of these curves have length A. And so the problem is to show that these are the maxima, and so the main difficulties are 2, as I was saying. So one I was mentioning. So one is to show that the orthosystole function admits a maximum. And once we know that, to prove our theorem, considering that we can construct these surfaces and we can compute this A, and this A is going to be this function FGL that I had in the statement before. What we need to show is that if we have fewer orthogeodesics than a hexagon decomposition, so if the ortho-kissing number is less than the maximum possible, so what was that? It was 3 times the Euler characteristic of X, then X is not a local maximum. And this is, so once we know that, essentially, you know that the only possible candidates for local and global maxima are those where that have hexagon decompositions, and by the computations above, you essentially figure out that they all have exactly the same length, so you are done. Okay, so this is a bit the ideas of what goes into the proof of the first part. For the second part, so what we use is a lemma that tells us what happens in the case of signature G2, where the 2 boundary components have the same length. The point is that this is a nice and symmetric situation in which we can find a hexagon decomposition of orthosystoles. We can find surfaces with a hexagon decomposition of orthosystoles, and we can compute the orthosystole length in this specific case in terms only of the length and of the genus, similarly to what we've done before. But so the main problem for n at least 2 is that in general, we do not have hexagon decompositions of orthosystoles. So we cannot play in the same game and getting the good candidates that we had before. We do not have surfaces with hexagon decompositions of orthosystoles. And this, essentially the idea is follows from what I said before. So before I looked at the case of one boundary component, and I knew that this boundary component was given by pieces of this length alpha. So if I fix a hexagon decomposition of curves of the same length, my boundary component is going to be given by a bunch of pieces of length alpha. And now in general, what we'll have is that if I have n boundary components, and I have a hexagon decomposition of orthosystoles, each boundary component will be split into pieces into some integer times the number of times this length alpha. So these boundary components cannot be anything. In particular, their quotient needs to be a rational number. So in general, there's no way of making this happen. And so the way we can use these results, so use the fact that in genus, for 2 boundary components, we have these nice surfaces with lots of orthosystoles and with large orthosystole length, is the following. If I now fix a surface of genus G with n boundary components, I can write G as Q times n plus R, so R, so R is the remainder, and sorry, less than n, and Q is the quotient. And I can write this piece, this is a union of surfaces y1, y2 until yn. So each yi have signature. So the genus is Q, and there's 2 boundary components. And then there's a central surface which glues them together. So Z has signature. I have n boundary components, and the genus is whatever's left to make the surface. So have the correct genus. This whole, if I glue these together, I get the surface of the correct signature. Here I can choose the YI so that their boundary components have length Li, both of them. So this is L1 and L1, L2 and L2, and so on until Ln and Ln. And then actually choose them better. So I choose the YI with hexagon decomposition of orthosystoles. So these are given to me by the previous lemma systoles. So what is essentially left to prove is that the orthosystole, so now this gives me some surface X, is that the orthosystole of this full surface is the minimum for I from 1 to n of the orthosystoles of the YIs. So for these YIs, I can compute what's the minimum. And I have an explicit formula above this one here. If I can show that, I get an orthosystole, the orthosystole length of my surface. So this gives us surfaces that have large orthosystoles. This won't have, in general, a hexagon decomposition of orthosystoles. And in cases in which such a thing exists, we can actually do better. So we have some constructions of some specific genera and some specific boundary lengths and some specific number of boundary components in which we can actually get a hexagon decomposition of orthosystoles. And in those cases, we get surfaces with larger orthosystole. And as I was saying before, we can show actually that these surfaces, these X here constructed like this, are not even local maximal for the orthosystole length. So maybe my main point is that in the case of multiple boundary components, we still don't know a lot of what's happening, and it would be very nice to come up with a better picture. And I think it's a good time to stop. So thanks a lot for your attention.
Thank you very much, Federica. It was very nice. Sorry. Are there any questions or comments on Federica's talk? If you have any questions, you can write them down in the chat. It's open. No, I see no hands. So I can ask you a very simple and stupid question. When you drew this torus with two boundary components, and you pictured, were there 4 curves, right?
6.
Oh, 6 curves. Can you? Oh, your Google Play stopped.
Good.
Okay.
Yeah, fine.
Can you draw the hexagons?
Yeah.
Can you help us for those that have bad imagination?
So, okay, let me find the page again. Oops.
I mean, it's a very clever exercise for topology, right?
Yeah, you just kind of need to go
page 3. Yes.
through that. Okay, so so the way I have is I try just to kind of follow So I know that I need to follow in this direction.
Yeah, there, one.
And then I go here, and so I'm already
Yes,
have
a
two
short
boundaries.
one, yes. Okay, along the boundary.
And then
Good.
here,
There.
so then I come back.
Ah, then you come back. Okay. Yes, okay.
Yeah, I think it's on this side.
Yeah. Then you go
then
along
there,
the boundary again.
Then you come
Yes.
back. And
4,
then you come up
5.
here. So you're on this side, and you come up on this side.
And then you join
close
on
it
the
up.
other boundary. Okay,
Exactly.
excellent. That's
And
the
then
6.
you
Okay.
same way you do for all of them. Yeah.
Okay, thank you. It was hard for me to imagine at first.
Yeah, I'm surprised I managed to draw it the first try.
Very good. Anything else? Maybe something less naive than my question, please. No, everything is okay. So thank you very much, Federica.
Thanks.
Thank you again.